My friend, now I have updated this convenient window who show the prediction and target and correction ratio and so on for the convolution neural network in C++ with no machine learning library involved. So I will go through the code. You will find the code in this repository, and I work in this folder for a moment with OpenCV. So we could jump into the code with respect to all this window and explain the code briefly regarding this. So we'll see. Let's work with the main. Look at the main program. Here we see the convolution class, and that's here we see the interface of the convolution class. Here we have convolution forward, clear the delta, convolution back prop, update weights, convolution forward, and that is our this is our forward representation. Then we call that function as well as this. So I will go through that. And then we have our class for the fully connected neural network here. You could set different kind of settings. Jump back to the main. So we instance the convolution layers and the fully connected neural network layers here. Alright, here we set up the structure who will be printed of the convolution setups, and you can change that. And then we have the fully connected neural network setup here, and then we prepare our data, MNIST data set. I haven't done yet 3 channels for the OpenCV data set. Here we set the hyperparameters, and here we load the saved weights. Here we set up the memory map for the OpenCV, and here we start to training, and we can begin with look at the image. So this is the input data. I think it's stopped now because it's during the verification stage. So now I think it's jump back. Yes. So this data is put in to the input tensor here of the first convolution stage, running the convolution forward, take that tensor into the second convolution stage. This and then we do our back propagation of the fully connected and so on. Here we enter the fully connected layers with the data from the convolutions. We do forward path of the fully connected neural network, and then we start to do back propagation from the loss error value. Here we do back propagation through the convolution, and then we start to do OpenCV visualization, and I could show that. So first of all we have this input image, and that is here. Each 100 sample is printed out, so this running much faster than the visualization here. That is the image we showed there. Then we put in our output data from, let's see, convolution stage 2. This data is the data who enter the fully connected neural network. But now I want to show how does that looks when I upsampling it. When I do upsampling this data back to the top and visualize that. So I take the output tensor and put it back to I borrow memory from the back propagation here. You see that memory here I borrow, because that's already done here, so I don't need that memory anymore. So I could borrow that, put in this data, and propagate backwards. Propagate that through the transpose function, and the transpose function is actually the same pattern in the same algorithm, I would say, as doing convolution back propagation, but you do not need to do the kernel delta calculation. You just skip that part. So it's convolution transpose is actually the mirror of convolution forward, and if you want for an autoencoder or so, maybe do backpropagation through transpose forward. That's the same pattern as do backpropagation of a regular downsampling. So it's kind of the mirror of itself. Anyway, where was we? We was at put in that, and then I do this loop and show the output image here. So this is the preparation of doing this image. All right. Then we step to next. Make upsampling visualization of single kernels. Yes, kernels, single kernels is here. So now it stops again because it's in there. Yes, we'll see. So this is made here, and what I've done here is that I take similar to the when I upsampling the whole thing, but now instead of taking these data, I set all the data to 0 here on this row of code, and then I select and then I touch the center pixel to 1, and I want to see that upsampled. So this is this square is the upsampling when I touch the center near the center pixel with 1 and the rest 0, and so on. All right, and then the next is convolution L1 is here. That's that code, and then we have convolution L2, that's this one. Can skip that. So this is here, and that's so. Then this image is here, and that's there. And then we could go to the kernel prints. I do the kernel 1 here. This code is this one, and then we have the second kernel is showed here, and then we have at last we have this one, who I called at this class. Sorry, at this function I called here. So that's the thing. And if you want to change, let's say you want to change your structure of the whole network, I stop there for a while, and let's say we change our structure of the whole of the convolution neural network part. So I begin here. Let's say we have 7 there, and we have stride 2, and we set this to we set this to 60, and we set this to stride 3, and this to have this to 5, and we set this to 7, stride 2, and 30 there, right? And maybe I also want to change the activation code from rectify linear on the convolution to sigmoid. Then I change that. If you look at here, we see the 3 modes I have on activation: sigmoid, rectify linear, and rectify linear with leak activation. And it seems to be when I switch over to sigmoid, I need to start with a higher value of the randomization at start. So we can start this. We can test that. And sigmoid function is more stable, but is not as fast to train, I figure out. Rectify linear could be unstable, so you may need here we see that we have 4x4 at the end of the convolution state, and 16 depth, and we see that we have kernel size 7 instead of 5 as before. We can compare that to here we have kernel size 5 and 30 in depth and 5x5. All right, so let's see, and I start from scratch, and then we see that it looks like this. Now we have 4x4 at the end of the convolution, and we see that it's slow converge at the beginning of the first epochs. Something start to happen in the representation here. I pause this and put in when I have run a full now we see the converging start to happen things there, but I could show when I put in saved memory from the whole epoch. Now we see it have run 10,000 samples. It seems to start slowing to converge, but when you're using Sigmo it's slower to learning. Anyway, not a number running away. It seems not to be a problem, but you have other issues with Sigmoid. It's pros and cons as usual. So, here's my lovely bunny, and we see now it have run for about 2 epochs. And well, you see it seems like a better representation here, and I think that's enough for today, and hope you enjoy to see that, and have a nice day. Bye bye.